everyone, welcome to session 3 of our Quadratics Masterclass. Today's lesson is going to focus mainly on solving quadratics via the factorization technique. If you believe that you're 100% ready for today's lesson, you've looked at the previous 2 lessons, then why don't we discuss the objectives for today's session. In today's session, focusing on the factorization process, you should be able to use this process by the end of today's session to solve absolutely any quadratic as long as it can be factorized. By the end of this session, you should be able to identify anytime a quadratic can be easily factorized, thus enabling you to use the factorization process to solve that quadratic equation. And we're going to take a look at the use of algebra tiles to help us with understanding how the process of factorization works. If you don't have algebra tiles and you are quite alright with working with the algebraic processes, you should be just fine with being able to understand how the process works. So let's get into the process of factorization. When we work with quadratics, remember that it's important for us to be able to identify the constant and the coefficients in our quadratic. And this is one of the reasons why it's important. In the factorization process, I want you to pay attention to the outline of the process here. Here we have the quadratic 3x squared plus 4x minus 4 is equal to 0. We know we're dealing with a quadratic equation immediately. In order for us to begin our process of factorization, notice that we must be able to recognize the coefficients of x squared and x respectively, as well as our constant. Here we list out the values of a, b, and c as per the equation that we were given. So we have a as 3, b as positive 4, and c as minus 4. The next thing that we do would be find the product of AC. In finding the product AC, we're just going to take the values A and C and multiply these two. Now, this is where our directed numbers come in, and finding the product of 3 and minus 4 gives us minus 12. So ensure that you remember the rules for doing products of negative numbers with positive numbers, or in general, just knowing all your rules, because sometimes you might come across some involving two negatives, a negative and a positive, or just simply two positives alone. Now, the tricky part of this entire procedure really comes in, again, involving directed numbers. But what we do at this particular point, we ask ourselves about a pair of factors of minus 12 that will in fact give us the same exact product of minus 12. However, if we were to consider summing the pair of factors that we took, we should be able to get the middle term of our quadratic. So essentially what we're doing here is we must find a product of factors that gives us back the product of AC, but we must also be able to take those same two factors, add them together, and get a sum that is equal to B. I have a product of minus 12 I need to obtain, and I usually encourage my students at this point in time to start off by considering every single pair of factors that you know can give you the number 12. Once we could start off with getting those factors, we could play with the signs after and kind of figure out what we need to do. So let's start listing out pairs of factors of 12. You can start off from 1 by 12, and then we have 2 by 6, 3 by 4, and we can stop right there because we know that it just mirrors itself as we progress forward. As you can see from the solution lines, we did in fact use 2 and 6, but here's how we came up with the decision to make 2 negative and keep 6 as positive. We can immediately rule out 1 and 12 because while we can get the product 12, we can't add them in any way to make positive 4. And likewise for 3 by 4, yes, we will get 12 again in the product, but in finding the sum or the difference of these two numbers, you would either get 1 or 7, so we can't work with this pair. But 2 and 6 I could use, because if I were to just say take away 2 from 6, I can get 4. And the same way of writing 6 take away 2 in terms of directed numbers would be to add negative 2 to 6. And that's how we will be able to get a sum of 4. And at the same time, still get back our negative 12 product. So this is the reason why directed numbers is such an important part of doing these procedures. So now that you understand where we tie things together in terms of getting constants and coefficients and then our directed numbers, once you can do this part here, the rest of it is going to involve the factorization itself. So we're going to be using this particular sum that we've constructed right here. We're going to use this in a short bit, and I want you to pay close attention to what we do at this stage, because most times students have a challenge at this particular point because they don't understand probably what is really transpiring. They just know the process itself. So let's move to the next part of things. Remember, we had the sum of -2 and +6, and we said this should give us back +4. Now we wanted to ensure that this sum really and truly gave us back the numerical value in the middle here, the value of b. The reason for doing that, I want you to take a very close look at this next line. I want you to take a very, very close look at this next line, and I want you to see for yourselves where the -2 and 6 come in. Notice -2 and +6, we're using them as coefficients of x. So there's a way in which I would refer to how this becomes what it is. And essentially, you can think about it in a couple ways. One is that if I want to make back +4x, essentially I have to break it up into the sum of +6x, -2x. Or another way of looking at it is that I replace the +4 with the sum of my two numbers that I came up with. So we replace +4 with -2 plus 6, and then we can expand this with distributive law and we'll get the same statement that we have here. Okay, so you have your options where you just need to know how do you replace this +4 in. So you have your options in terms of how you can replace this +4 in the quadratic equation. Now once you do that, this particular part is very significant. We need to be able to do this piece so that we can do our factorization by grouping, so that we can start to do the complete factorization of our quadratic. So let's go through our procedure to do our factorization. The first thing is I'm going to do factorization by grouping by observing the first two terms in my equation, and I have 3x² plus 6x. Now, yes, I did in fact write it in this way to make it a little easier for me to factor out the highest common factor from the very beginning with my terms. So factoring out 3x from these two terms will give me my factor of 3x to the side, and then in my binomial I'm going to have x plus 2. Okay, so remember, you need to be able to factorize by looking at these terms, identifying the highest common factor, and we can see that the highest common factor, the coefficients have a common factor of 3. Because we have x² and x, we have a factor of x. So this is how we get our highest common factor of 3x. Now let's look at the second pair of terms that we have in this expression, and we'll factor out -2. Notice we have a factor of -2 common between the -2x and the -4. Now, this is something that happens a lot because students see that we factored out an x here. They sometimes think they have to factor out an x here as well. Remember, you're paying attention to what is common between your algebraic terms. So here I have -2 only being a common factor to both terms, and this is the reason why we only factor -2. Now, sort of shortcut, to always remember is that with complete factorization, we need to ensure these binomials are in fact identical. So I'm going to either one and two things. Keep this in mind while I am factorizing my second pair of terms to make sure that I know that my binomial ends up looking like this one. Or I could probably start it in a sense reverse and put down my binomial first and then ask myself, okay, what do I need to multiply x by to get back a minus 2x, and what do I need to multiply positive 2 by to get back a minus 4, and I'll still get the answer. So this is the first step in doing our complete factorization. And once we have that first step done, the second part now is to recognize that the binomial is in fact our common factor. Can we see that we have x plus 2 in both of these, what I would refer to larger algebraic terms? Because you can see for yourself here, this is a difference of two algebraic terms where you have a binomial factor involved. And here, if I pay very close attention to the fact that binomials can in fact be factors as well, I can factor out this binomial factor, and this is how we will get our final line of x plus 2 into 3x minus 2. So some of the things that many students might have heard is, the little shortcut ways. You take what is outside the brackets, put it in a bracket, and then the other brackets, you just multiply by that. Whichever way works for you, you just do what you need to do. But for those of us who need to fully comprehend the process of factorization and need to know that this is a factorization still occurring here to fully appreciate what is being done, remember you are factoring out the common factor, which in this case was a binomial factor of x plus 2. So when we factor it all out, this is what we get: x plus 2 times 3x minus 2, and because we were dealing with an equation, we have that it is equal to 0. So we're going to take it even further now. We wanted to solve for x. We wanted to get the values of x, which will make this quadratic 0. And when we do this particular part of the procedure, I want you to also observe that it is very important to understand when can a product be equal to 0. Now, I have my binomial product of x plus 2, 3x minus 2 equal to 0. I need to find the values of x for which my quadratic is equal to 0. Now, if a product is equal to 0, all right, so ignoring the fact that you have a pair of binomials here, I want you to just think about, simple cases. If you just had a product of two arbitrary constants, right, and the product is equal to 0. Essentially what that indicates for us is that either one of these would be equal to 0. That is, if A is equal to 0, the product could be 0, or if B is equal to 0, or if B is equal to 0, this product will also be 0. So essentially, when you have a product that is equal to 0, either one of the terms can be 0. And this is the reason we approach solving a quadratic through factorization method like this. We start off by considering either one of these particular binomials being equal to 0, because we just said that when we have a product equal to 0, either one of the terms in the product is equal to 0. So we start off with either x plus 2 is equal to 0, or we can say 3x minus 2 is equal to 0. And from here, what we're doing is attempting to make x the subject in both of these two expressions. Now, I want you to pay attention with using the binomial factors as the expression on the left-hand side. What we in fact created here by putting a binomial factor equal to 0 is a linear equation, something that you have met before. This is prior knowledge, being able to solve a linear equation. And what we do here to solve for x in the linear equation is transpose. So if you are strong with linear equations and you are strong with transposition, you will have no trouble at all with being able to transpose these equations to solve for x. So from here now, all I'm going to do is make x the subject in both of these equations. And what that gives me is, in the first case, I have to subtract 2 from both sides. Now again, I know many students might have learned it as you're just carrying this to the next side and whatnot. Whatever helps you remember how to do procedures, by all means, go right ahead. But if you want to be able to understand what is transpiring in this particular process, remember when you deal with equations, you are keeping something in balance because both sides are equal to each other. So whatever you do on one side must be done on the other side. And this is what will give us in the next line, x is equal to 0 minus 2 because I subtracted 2 from both sides. So this is how I will get my answer of x is equal to minus 2. Okay, so that's the first solution. Now we have 3x minus 2 is equal to 0. And for us to be able to solve for x in this case, again, we're going to start off first of all by subtracting. So we're going to start off again by adding, in this case, adding 2 to both sides. So we'll get 3x is equal to 0 plus 2. And now that we have 3x is equal to positive 2, we need to make x the subject. And because we have a product of 3 by x, we need to divide both sides by the coefficient 3. So this is the reason we will get a final answer. So this is the reason we will get a final answer for x in this case as x is equal to 2 over 3, 2/3. So our final answers for this particular quadratic, we get x is equal to minus 2 and x is equal to 2/3. So that's what the process of solving a quadratic via factorization method entails. And once you understand all the little tiny bits in the process, you'll be able to solve absolutely any quadratic. Alright, so the key things to remember when solving a quadratic, you must always ensure that you can identify your constants and coefficients from the very beginning. You can work with directed numbers. As you all can see, directed numbers is such a very integral part of what we are doing here. And then we also need to be able to do our things we also need to be able to do things like identify highest common factors among algebraic terms, do our factorization, and finally solve for linear equations, solve for x, transpose for x. So that's what this procedure entails. Many tiny little things, but ultimately you can achieve the overall objective of solving a quadratic using factorization. Now, aside from using the factorization process through the algebraic technique we just did, I'm going to demonstrate how we can factorize a quadratic using algebra tiles. This is merely for the purpose of demonstrating so that those who have some trouble with the algebraic process can in fact think about it in a very visual perspective and probably be able to make that connection as to what the factors of our quadratic can represent in a sort of real life scenario if we were to be representing our quadratic using algebra tiles. Okay, so the solutions for our quadratics, let's take a look at the solutions. So here we go. So for the very first quadratic, the factorized form is x minus 1 times x minus 2. So if we wanted to solve this particular quadratic, remember we start off by recognizing a, b, and c. And from here we can see that a is positive 1, c is positive 2, and b is negative 3. So we use a and c to get a product of positive 2. So AC is equal to positive 2, and remember we want to get a product of factors of 2 that can still give us positive 2. But if we were to add them together, we should get negative 3. And immediately there's only one pair of factors that we can use to get positive 2. And if we want to get a sum that will give us -3, well, we need to make these two numbers negative. So our factors need to be negative here. We use a product of -1 by -2 to give us +2. To use the sum of these two numbers, we would get -3. Okay, and once we do that, we break up our middle term into the sum of -1 and -2. And from here you can see that you have a common factor of x between the first two terms. So I'm just, skipping down a line just to demonstrate. And we'll have x into x minus 1. So you've seen that first factor already there. And then between -2 and +2, we'll have a common factor of -2. Remember, like I was saying earlier, shortcut, you want to make sure that the binomials are in fact identical. Okay, so we factor out a -2. And then from here, we will just factor out our common factor of x minus 1. And these two guys get put into one binomial factor, and that's where the x minus 2 comes from. Alright, so this is how we got to this point. Now, if I want to solve the quadratic, time to solve the quadratic, we have the quadratic expressed as a pair of binomial factors. And what do we do from here? So if you can recall correctly, we're going to consider when each of these binomial factors is equal to 0. Alright, so let's consider when each of them, so now we consider when each of them, is equal to 0. And from there, we'll be able to solve for x, and we'll get that x is equal to 1 or x is equal to 2. Alright, so just for you to be able to make your comparison here with the second quadratic, we know what the procedure of solving the quadratic entails. So the solution in this particular case, I wanted to highlight something. In this solution, you'll notice that both the binomial factors here are the same, they're identical. So in a case like that, this is what we refer to as a perfect square, and it's one of the forms of a quadratic that you can find. When you have a perfect square, one of the things that you need to know is that the solution is going to be the same value. So if we were to solve for x, notice that I did not solve for x in both cases simply because both my binomial factors are identical. So I'll only get one solution, and make note at the bottom here, for a perfect square you can express the binomial product that is the factorized form of the quadratic in this particular index notation. Okay, so this is something that you will also notice when you deal with quadratics. You don't have just general quadratics, you have perfect squares and you have difference of two squares, and you need to be able to recognize these. Okay, now the method of factorization, the process that I showed you, you can use that method to factorize absolutely any quadratic. Does not matter whether it is a difference of two squares, perfect square, or just a regular quadratic. The process is still going to give you the same exact way of coming down to the solution. Okay, it's just that with a quadratic that is a difference of two squares, yes, there are some shortcuts that many people would have learned. And for this reason, if you are quite familiar with that and you don't mind working with that particular way of factorizing a difference of two squares, by all means, you can do that. Okay, so this is how we use our process of factorization. And in a short bit, I'm going to just demonstrate what it is like to use algebra tiles to do our factorization. So again, I have another pair of quadratics that you can use for practice, and I'm going to put the solutions up so you can see the final answers. You'll be able to compare your final answers. And once you understand the process of factorization, you should be able to get to these points. So that's the solution for the very first quadratic. And then in the second quadratic, I really want to skip to this one because this one is what I was talking about earlier. It's what we call a difference of two squares. At first, it does not look like that, but I want you to pay attention to the fact that you can factor out 5 from both of those terms, okay? So you can factor out 5, and when you factor out 5, what you get is 5 times the product of x squared minus 25. And the reason we call this the difference of two squares is that if you look carefully here, you'll notice you're finding the difference between two square terms. So that's what makes it a difference of two squares. Now, if you want to solve again, you can factorize this using the same process that we have been using for the entire time. And I'm going to demonstrate how we do that with a difference of two squares so you will understand how to work with it. Now, this one might seem a bit tricky to people if you have to do the procedure because you don't have a middle term. But if you don't have a middle term, you should understand that means that b is equal to 0. So if you don't have a middle term, you should understand that b is equal to 0. Since b is equal to 0, you'll see how this affects your factorization. So from here now, I'm going to find a pair of factors that I can multiply. That will give me minus 25, but at the same time give me a sum of 0. Now, it's a no-brainer. 25 has two possible pairs of factors you can work with. You can use 1 by 25 or you can use 5 by 5. And one that makes sense here is 5 by 5 because we want to get a sum of 0. So the only thing that I need to figure out is whether or not the signs remain the same or do I change these signs. And obviously if I want to get a difference of 0, and obviously if I want to get a sum that is equal to 0, one of them has to have a different sign. So positive 5 by a negative 5 is going to give me the negative 25 I want, but if I add them together I am going to get 0, and that's what I want. So factorizing, I'm just going to express my quadratic in terms of this difference here now. So I'm introducing my replacement for my non-existent middle term here, and I'm going to get x squared plus 5x minus 5x minus 25. So you would have noticed as well that when we got to x squared minus 25, although there were two terms in that expression, we still couldn't factorize it with highest common factor. So that's how you know, again, when you deal with a quadratic, you have to resort to this factorization process that we're using. So now what I'm going to do from here is do my factorization by grouping, and I will be able to solve for this quadratic. So I'll get common factor of x between these two terms in my expression, and we'll get x into x plus 5. Now I'm going to repeat the process here, and this time I notice I have a common factor of minus 5, so I get minus 5 x plus 5. We're almost done with our factorization. We just need to express it as a binomial product now. So we have 5 into x plus 5 that's a little wonky there. X plus 5, x minus 5. Okay, and from here we'll be able to get our solutions. and we will get that x is equal to -5 or x is equal to +5, as you'll see in a short bit. So this is how we do the factorization process that we just did on a difference of two squares, and I will explain the other process as well in a short bit, but at least you can see for yourselves that the typical process that we just looked at can be used to factorize a difference of two squares. So again, notice first thing, factoring out our common factor of 5, and then factorizing our difference of two squares, we just find the square root of the terms in the expressions. So the square root of x squared is x, and the square root of 25 is 5. And this is how we can establish the terms that go into our binomial. They're going to be identical, except the sign in one will be negative and the sign in the other will be positive. It's pretty much the shortcut way of doing this, and if you understand how to use the shortcut process, it's by all means acceptable. Alright? Then from here, we have to solve for x. Let's just talk about how do we recognize when we can factorize a quadratic. There are times when you'll make quadratics which cannot be factorized at all. And being able to recognize A, B, and C and that very first stage of our factorization process, in fact, can tell us whether or not we can factorize a quadratic. Simply put, if it is when you identify A, B, and C, it's not possible for you to get a product that will give you back AC and also give you a sum that gives you your middle two. Alright, so from the time you start to have challenges with being able to identify a sum that will be able to work as well for a product of factors that can give you back AC, then at that point in time you may have to opt for another method to solve a quadratic, and this is where your quadratic formula will come in. So we'll take a look at the quadratic formula in an upcoming video, but this is how you can tell whether or not a quadratic can in fact be solved. So for example, let's just say I had a quadratic Is it possible for us to solve this quadratic by factorization? Well, let's take a look at the coefficients and the constant. In this case, A is 1, B is -5, and C is positive 10. So if I find the product of A and C, I would get positive 10. Can we identify a pair of factors that we can use to get a product of positive 10, but at the same time give us a sum of -5? The only pairs of factors that can give us a product of positive 10 would be either 1 by 10 or 2 by 5. And immediately you can see that using either of those pairs will not be able to give us a sum that will give us -5. So an example of a quadratic that you may have to use quadratic formula on will be one like this. So we will be taking a look at quadratic formulas soon, and you'll be able to understand how to use your quadratic formula to solve quadratics. Essentially, this is a procedure involved for factorization, and I'm going to demonstrate the process of using algebraic tiles to get a factorized form of a quadratic in a short bit. So stick around for that, but if you feel like you fully understand how to do the procedure of factorization just fine, you are more than welcome to go ahead, get some more questions, practice, and see how much you can do on your own with factorization now. Now let's take a look at using algebra tiles to demonstrate how we do a factorization. What we have to recall is that in representing our quadratic expression using our algebra tiles, we are going to be using the number of algebra tiles specific to the term in the expression. The image here is demonstrating 4x squared plus 8x plus 4. Now, if we have to factorize this particular quadratic, what we're going to do is pay attention to the number of tiles making up the ends of our shape. As in, if we were to think of it as a rectangle and we wanted to get the area of the rectangle, we'd need to get the length and the width of our rectangle. Here, what makes up the length of my rectangle? 2x squared tiles and 2x tiles. Now, if I'm measuring the length of this particular shape, I'm going to count the lengths of each of my shapes making up the length. So here I have 2x squared tiles, which means that the lengths of these would be x each, and for the x tiles, those would have a length of 1 unit. So here I have a length of 2x plus 2, and you'll notice that we have that on both ends. So both the sides of my overall shape would have a length of 2x plus 2. So if I factorize this, what I'm essentially doing is finding the product of the lengths of my shape. So this will give me a product of 2x plus 2 by 2x plus 2, and thus we have factorized our quadratic. Essentially, using algebra tiles, we are letting the area of our shape represent the quadratic. So when we find the product of the length and the width of our shape, we're finding the completely factorized form of our quadratic. Now that we've come to the end of our factorization, let's take a look, make sure that we understood what was expected of us, and to ensure that we have in fact achieved the objectives for today's session. So, do you know how to use factorization technique to solve a quadratic? Regardless of the type of quadratic, whether it is a perfect square, a difference of two squares, or simply a regular quadratic, can you use that factorization technique? And if so, great job. Now, can you tell when it's more appropriate to use factorization? I hope you can. I hope you remember what we said about being able to identify whether or not a factorization process can be applied. Alright? And when it came to the factorization of a quadratic using algebra tiles, do you think you comprehend how to use these wonderful little tools to help you with doing your factorization? If so, you've achieved the objectives of today's session, and you can proceed to the next parts or to the next lesson that is most appropriate for you to continue. Did you enjoy this particular session? If you did, be sure to leave a thumbs up and share with your friends as you guys prepare to write CXC exams. Be sure to tune in for future videos as we continue our masterclass series in quadratics. Thanks for watching.